So today I want to go over the heat of fusion lab that we did in class. It was called the melting iceberg, which is pretty clever pun on what's going on. So what we want to know is find out how much heat does it take to melt ice. So we want to find out the heat of fusion of ice. And we're going to take advantage of something that we already know, which is the heat of how much it takes to raise the temperature of water. So we're going to use delta H is equal to M C delta T. So remember, M is mass, and in our units we've been using grams. C, we're going to use specific heat, and then we're going to have the change in temperature. So here's our setup. We have two things initially. So we have ice cubes that are ready to melt. So here's my ice cubes, and I know they're ready to melt because there's already a little bit of water that's already coming off of it. And it's important to understand why it's ready to melt. Is that I don't have a thermometer that I can stick in here to measure the internal temperature of the ice. So I'm going to make an assumption here that when you start seeing water or it melting, is already changing from solid to liquid, that this is going to be at 0 degrees Celsius. Now, it's going to be a little bit off just because the inner part of the ice might be a little bit colder. The outer part of the ice might be melting already faster than we can measure it. But we're just going to say on average, we're going to try our best to get it to 0 degrees Celsius. That's our assumption here. Then in my other cup, I'm going to have water, but I don't want it just room temperature. I want it warm enough to melt all my ice. So I'm going to, let's say in our lab, at least in one of our examples, we have it at about 50 degrees Celsius. So it's pretty warm, not yet boiling, about halfway there, but it's not room temperature, which is about 23 degrees Celsius. So we have about 0 degrees, 50 degrees, and what we're going to do is we're going to add it together, and what we want to find out is after all the ice melts, what's the final temp? And once we find the final temp, we could calculate how much heat was lost on this one. So this one's going to lose heat, and this one's going to gain heat. And we want to know how much of each one is going to eat. And what's cool is that this lost heat is going to equal this gain heat because they're going to eventually get to equilibrium. So that's our goal. I probably shouldn't have put an equal sign right here. This is more of an after, so I'm going to kind of erase that. So you add them together, and this is the after product because technically it's the heat that's going to be equal. The gained heat is equal to the lost heat. I'm going to put absolute value here so the signs are going to be the same, but that's our goal here. All right, so in our example, let me just make up some data points. So let's say, mass of empty cup. I'm going to make it easy on myself. 5.0 grams. Mass of cup plus warm water. Let's make that easy for ourselves too. Let's say 85 grams. Let's see. Temperature of H2O, I stated was 50 degrees Celsius. And then equilibrium temperature. Let's see, I'm making up these numbers, so I want to try to make it at least realistic. Let's see, 5 grams. So let's say about equilibrium temperature was about 10 degrees Celsius, and then mass of cup plus warm water plus melted water equals, let me see, so I'm going to make up a number about 40, yeah, let's say about 40 grams. So I made up these numbers, so our final answer is going to be a little bit off, but I did make these off the top of my head. All right, so how do we solve this? Well, we're going to go the delta H of the warm water lost is going to equal the delta H of fusion plus delta H of the ice going up to equilibrium. And what do I mean by that? So what's going to happen is we added enough warm water that our goal is to melt all the ice. Well, from the time where the ice is melting, so when ice becomes H2O, when you're going from solid to liquid, there is going to be no temperature change because all that energy inputted into ice is changing the state of phase. So there's nothing here. But let's say our equilibrium temperature is 10, so that means then we're going to have amount of the ice, then it's going to have to warm up to 10 degrees Celsius. So energy was used to melt, plus energy was used to raise the temperature. So that these two together is going to equal the amount of heat lost from this one. All right, so let's put that together. Let me get a new color, so separate it. So heat of fusion is what we're looking for. This is the question mark. We do know this one, right? Delta H is mc delta T. And then this is going to equal to this one, which is mc delta T as well. Let's plug in what we do know. Mass of the ice was, let's see, 140. Sorry, I meant to say, kind of messed up here. I meant to say 40 plus 85, so 125.0 grams. But you kind of say my ideal mass was 40 grams. Specific heat of water is 1 gram per, 1 calorie per gram degree Celsius times the change in temperature, which is 10 minus 0. Final is 10 minus 0. And that's my left side. My right side, my mass is going to be 80. So 85 minus 5. Specific heat is still 1. And the change in temperature, in this case, it's going from 50 to 10. So final is 10 minus 50. So like I said, this is going to be negative because it's lost, but we're just going to make them the same because what we're doing is not comparing the amount of energy as a system. We just want to go, okay, this one's going to lose. That's why it's going to be negative. This one's going to gain. That's what's going to be positive. I just want to compare the quantity of amount. So where I'm going to ignore the loss versus gain. So when I do that, this one's going to be, let me get my calculator. Oh, where did my calculator go? All right, I'll be back. I think my son stole it. All right, I found it. So my son realized that he could do his math homework with my calculator now, and he refuses to learn simple math and tries to use my calculator all the time. And he's only 5. All right, here we go, because I can't do simple math anymore. So 40 times 1, oh, I could do that one. So this one is delta H plus 400 is equal to 40 times 80, which I'm going to be lazy, even though I should know the answer. 3,200. So remember, these are equal just because the heat loss is equal to the heat gain. I'm going to move the 400 over to the other side. So my delta H of fusion is equal to 2,800 calories. Now we had a certain mass, so if we wanted it per gram, so we're going to divide it by 125. Actually, we're going to divide it by mass, look up with HO. We're going to divide it by 40 grams. So we're going to get an answer of calories per gram. So let's see how close my, oh my gosh, I'm amazing. 80 calories per gram. So that's actually the real delta H of ice. So I was lucky enough to kind of fib my way through it and actually get the real I guess, accepted value. So here we have an example of melting ice, raising it to a certain temperature after you mix it with warm water. We could do another one here. And in the other example problem, we have, let's see, 2.4 liters of water at a temperature of 24 degrees Celsius. We want to know how many 24 gram ready to melt ice cubes are needed to make ice water. So what I'm going to do here is I'm going to add one thing. How many? At least So what I want to do is I want to find out at least how many ice cubes I need in order to make this ice water. I could throw in a ton of ice in there, but let's kind of be efficient with it. So we have 2.4 liters of water. And we want to, if we want to get ice water, right? If we're getting ice water, this 2.4 liters at 24 degrees Celsius, if it becomes ice water, ice member is 0 degrees Celsius. So our goal is how much energy do I need to take from this one and transfer it to the ice cubes to get this, right? So this is going to lose heat and something needs to take it. So what's going to happen is I'm going to have ice cubes turn into water, and that one's going to gain heat. So what I want to know is how much of this ice I need to lose this much energy. So first we're going to do a delta H of my first problem. So I have 2.4 liters, which is also 2,400 milliliters. For water, it is 1 milliliter equals 1 gram. So I'm going to just do everything in my head. So remember, a liter is 1,000 milliliters, so that's how I got 2,400. And then a milliliter is a gram, so I got my mass. Specific heat is 1 calorie per gram degrees Celsius. And what I want to do in this place is to change my temperature from 24 to 0. So final is 0 minus 24. And here's my first equation. This one I do need the calculator. So 24 times 2400 is 57,600 calories. This is how much heat is going to be needed to take away or lose from the water to go from 24 to 0. So what I want to do is I want to make my heat of fusion equal to that, because that's the amount of ice I need. I know that for heat of fusion it's 80 calories. You need 80 calories to melt each gram of ice. So what I'm going to do now is, my goal is to get the grams, so all I have to do is divide. So if I divide this 5,700 divided by 1 gram over 80 calories, which is just the reverse of what I have here. So I just flipped it. The calories cancel out, and I'm left with grams. So divided by 80. So that means I need 720 grams of ice in order to make it ice water. Each ice cube has a mass of 24, so I'm going to divide this by 24 cubes, grams per cube. And then I get 30 cubes. So I need more than this to get ice water. So if I put in exactly 30 cubes in this fake problem, I'm just going to get 0 degree water. So if I want some ice water, I need to have at least 31 ice cubes. Okay, so hopefully that makes sense. Let me know if you have any questions.